Hi, brief calculus students. I just want to go over the derivative of exponential functions with you. I also do a recording for derivatives of log functions. Now, you're used to power functions. Power functions have the variable on the bottom, or the base, and the exponent itself is a number. And it raises it to a power. It tells us how many times to multiply. So this one would be x times x times x times x times x. It's 5 multiplications. And we have the rule that, there's a constant times x to raise to some power is the constant multiplied by the power times the x raised to the n minus 1 power. So we're working with the power. And, x to the 5th is 5x to the 4th. Derivative of 16x squared, or cubed, would be 48x squared. Square root of 3x would be, so square root is like a 1/2 exponent, so 1/2 minus 1 would be negative 1/2, which is why the square root comes down here on the bottom. So we've got 1/2 times 3x to the negative 1/2 times, this is the chain rule, the 3x, or the derivative of 3x, which is 3. And when we can even have decimal exponents, and it follows the same rule, we just subtract 1. Now, exponential functions have a number base, and the variable is going to be up in the exponent, and it does not follow the power rule. Quick vocabulary. The exponential function was going to have a number down here. That's why we're giving it a b. We actually call this the base. So the base number is going to be raised to a variable or even a function of the variable. But, the b is some kind of constant number. So when we take the derivative of an exponential function, so a times b raised to x, a and b are both constants, but a just comes along for the ride. We find the natural log of b, or the base, and then we just multiply by b to the x. You notice there is no subtracting 1 because we're not changing the power, the number of times we're multiplying everything. We're accepting the fact that this is the variable right here. So derivative 2 to the x is the natural log of 2 times 2 to the x. So I'm going to put these into the calculator. I'm not going to have them come up. So 2 raised to the x power. Because I'm going to do zoom 10, or zoom 6, so that's the 10 by 10 sort of thing. Zoom 6. And there we go. Yep, it's an exponential function. Now, in here, I'm coming in and putting in the n derivative. Math. Because I've got the 83, I have to come down to 8. Numerical derivative of variable, y1, work, comma, x is the variable, and find the numerical, derivative at all x's. So as I graph it, I know exponentials take a little bit longer. You notice that we still have this exponential function right here, this 2x. It's just being multiplied by a number that's going to slow it down. What is the natural log of 2? Let's see, natural log of 2 is a little bit less than 1. So you can see why that was getting pulled down. If we change this to 3, and I'm going to come here and change the line to, bold. So there's the 3 to the x, and here's the numerical derivative. And it's almost the same. Let's look at the table. Yeah, come on, table. So here at 1, we've got 3 and a little bit more than 3. Here at 2, we've got 9 and a little bit more than 9. So yeah, in fact, if we look at the natural log of 3, it's really close to 1. Alright, here, natural log of 10. Let's just look at that natural log of 10 right now. So it's going to be about twice as big. So let me do zoom 4. Oh, I forgot to change it. There's that 3 to the x. And natural log is really close to that. Let me change this. Okay, come on. Slow. Okay, there we go. So let me change it to 10 raised to the x power. So it's going to go up fast, and then, I think we're going to need to expand this window. As soon as that way, okay. Window, let me just go to 2 and change this one to, I don't know, 10. Graph. So 10 to the x, and it's going to go up almost twice as fast. Yep, you see how right there it crossed the y-axis really close to 2? That's because 10 raised to the 0 power, or 3 raised to the 0 power, or 2 raised to the 0 power is actually just 1. And so when we multiply it by this natural log of 2, then that's what it's going to go. 1 times the natural log of 10. 1 times the natural log of 3 times 4. In fact, why don't I do that? 4 times 3 raised to the x. That's going to give us something like 4. So this was the e to the x right here times 4, or 3 to the x. And boy, that natural log of 3 is so close to 1, it's really hard to see the difference between the numerical derivative and this function, or the original function that we started with. Now this function came up, people were saying, why in the world is this derivative? Well, pi is actually a number. We just write it with a symbol because it's a pretty long number. So on your calculator, it's just right here, all above my caret. There's pi. You can see it's just a number. So we can actually take the natural log of pi and get a number. So even though it doesn't look like the ones we're used to, it is a number. And so, I might as well move this over. We have a special case of a number that's actually given the letter e, because it is the quintessential exponential function. And pretty much the guy that discovered its last name was Euler, which sounds weird, but it starts out with the letter E and then U, and so this kind of name for him. And when we try the natural log of e, we just get 1, and so the derivative of e to the x is e to the x, which is really fun. So let me clear this. E to the x is right here above the natural log button because they are inverses. I'll just say e to the x. So zoom 4. So there's e to the x. You notice how it goes through 0. And then here we come with the derivative, and sure enough, it's tracing really close to the line. If we look at the table, you notice we've got the same numbers. In fact, e, second, there you go. E itself is a number that's between 2 and 3. Remember that the natural log of 2 was a little bit less than 1, and the natural log of 3 was a little bit more than 1? Well, e is right in between these two numbers. See, 2.718281828. It's one of those numbers that keeps going, kind of like pi. So, yeah, this is a really cool function right here. Do you remember the chain rule? The chain rule said we had a function of a function. The function was kind of tucked inside. Well, right here, the function is tucked in the exponent. Remember way back that few slides back, I said the exponent could be a function itself. So we keep the start the same. The constant stays there. We take the natural log of the base and rewrite the base with the exponent, the function in the exponent. But then we have to take the derivative of the exponent. So we just chain on an extra piece. So derivative of 2x, 2 to the x minus 1 is ln of 2 times 2 to the x minus 1. And this function stays the same. It's not a minus 1 like a power rule. It's just, I'm trying to point this out. Power rule and exponent rules are different. And then the derivative of x minus 1 is 1. So here we have 3 to the 4x. Well, natural log of base, then we have base to the same exponent, and then the derivative of the exponent. And some people like to multiply and rearrange and put the 4 in front. If you write it this way, I'm good, because then I can see exactly what steps you used. So here's a 10 to raise the x squared. So natural log of base times the function itself, 10 to the x squared. And then the derivative of x squared would be 2x. We're good. And then we can use it for multiplication and division rules. And this is my last example. So we just say the derivative of the first, this is the product rule, okay. Derivative of the first times the second, plus the first times the derivative of the second. And I did not write multiplication here because it's not always necessary. This type of equation, it is understood that it's 2 times t times e. So we're not trying to spell a word. So derivative of 2t is just going to be 2, and then this exponential function stays the same. The 2t stays the same for the second piece. Then the derivative of e to the 3t is e to the 3t times 3. So, there you go, exponential functions.